everybody, welcome back to Glaciers and Glacial Geomorphology and to Unit 4.2, in which we're going to be looking at glacier dynamics and morphology. Over the last few sessions we've been looking at how glaciers move. In this session we're going to look at how that movement relates to the overall shape or gross morphology of an ice sheet. Now, you've already learned in the last few sessions a lot about glacier dynamics, about how glaciers move. In particular, in the last 3 sessions we've been looking at internal deformation processes, creep, and you've learned all about Glen's flow law, the shear stress equation, and you've drawn vertical profiles of creep based on the vertical shear stress profile, creating your vertical strain profile, from which you created your vertical velocity profile. So you understand about internal deformations. You also understand about basal sliding, and you understand that shear stress is critical there again, particularly basal shear stress, the shear stress at the base of the glacier where you have that full thickness, H, of overburden pressure. You also understand the factors that mitigate against sliding, the friction or the roughness at the bed, and you understand the processes of regulation and enhanced basal creep that enable glaciers to overcome that roughness. In the last session we talked with Rich Waller about subglacial deformation, and you learnt about the deforming bed, the driving stress again which underpins that deformation or that movement underneath the glacier, and also the resisting forces and the things that mitigate against those resisting forces. So you talked about cohesion, and you talked about basal water pressure and water pressure within the substrate. So you've covered an awful lot of material already about glacier motion, so hopefully you're beginning to feel confident that you have a broad understanding of what's going on when we're talking about glacier dynamics. There's more for us to talk about yet, but I wanted to take a little bit of time out just now to think about an important implication of what we've been saying to do with glacier dynamics, extend it a little bit and talk about the relationship between glacier dynamics, which you're learning about now, and ice sheet morphology or glacier morphology, the overall shape, or in particular the profile of an ice sheet, and the interactions between the profile and the dynamics. So these few pictures illustrate the situations that you're now familiar with. We've talked about a rigid bed or hard bed glacier sliding scenario. You know what's going on there. You can imagine basal water pressure, friction, enhanced basal creep, regulation. We've talked about deformation within the ice, and this photograph isn't exactly what we were talking about with the creep internal to the glacier, but this shot of the basal ice layer at the bottom of the Greenland ice sheet, near the margin of the Greenland ice sheet, illustrates quite nicely that there is deformation going on within the ice, not just sliding of the ice across the bed, but also internal deformation within the ice, illustrated here by the deformation that you can pick up in the layers of debris within that basal ice. And most recently you've been talking about the deforming subglacial layer, and appropriately here's a picture of Dr. Waller in front of what quite well represents a deforming subglacial layer, even though I've cheated a little bit here. And again, you're actually looking at the bottom of the glacier on top of a frozen, a basal ice layer which is extremely rich in debris, but it gives you a nice picture of what we can imagine a potentially deformable subglacial layer looking like underneath the bottom of a glacier. So you're familiar with rigid bed, with soft bed, and with deformation internal to the ice. So you know a little bit about what's going on in terms of glacier motion. So in this session, and in the reading that you're doing around this session, what we're thinking about, and what I want you to read about and to think about and to hear what I have to say about, is the relationship between these ice motion mechanisms and processes that we've talked about and ice sheet profile. And in particular I'm going to talk about, and you need to look up and find out about, the idea of a perfectly plastic material and the concept of yield stress. Now, in explaining those and talking about those and how those relate to this relationship between motion and profile, we'll find that we have to say a little bit more about the role of water pressure, a little bit more about the role of temperature, and those are topics that we're going to come on to in the next few sessions in the module. And you'll also be thinking a little bit more, again, about the relationship between driving forces, shear stress, for example, and resisting forces, friction or cohesion, for example. Along the way, it should also become clear to you that we're now identifying some of the reasons that glaciers fluctuate, glacier margins advance and retreat, that are not climate controlled. A lot of glacier advance and retreat is climate controlled through mass balance, but also there are non-climatic controls on the positions of glacier margins, and we'll encounter a little bit about that when we think about how glaciers change their shape, including their extent, in response to changes in the basal yield stress, the shear stress therefore, and the factors that are included in that shear stress equation that you're familiar with, tau and tau b equals rho gh sine alpha. We're going to look at the terms in that a little bit, and that should help you to understand this relationship between morphology and dynamics. Now you're already familiar, I hope, with this diagram. It's come up in previous sessions and you've seen it in your resources, and it features in the books that I'm hoping you're keeping up to speed with. And what this diagram shows is the cross-section or cross-profile through a theoretical ice sheet surface, with the margin of the ice sheet on the left-hand side of the diagram, the centre of the ice sheet, the top of the dome on the right-hand side of the diagram. And the scale on the left-hand side shows you the elevation of the surface above the base of the ice sheet, so 0 at the left-hand side, where we're right at the margin, going up in this example to a 2-kilometre thick ice sheet. Then at the bottom of that scale, on the left-hand side, the scale changes, and we're just looking at metres there, not kilometres, to the depth of subglacial deformation, the base of the deformation layer, if we're looking at a glacier that has a deforming substrate. Superimposed upon that is a graph of the basal shear stress, which is 0 underneath the flat surface at the centre of the ice sheet. We've talked about that before. And then using the scale on the right-hand side of the diagram now, the basal shear stress climbs as you approach towards the edge of the glacier, as you increase the gradient, even though you're decreasing the thickness, then drops off again to 0 right at the margin, where we have 0 thickness. And again, that's something we've talked about before, but it's illustrated quite nicely on this diagram, showing the relationship there between the basal shear stress, which is controlled by the surface gradient and the ice thickness, but also there in that deformation layer, or the thickness of the deformation layer shown at the bottom of the diagram, you can begin to pick up the relationship there between the driving stress, the basal shear stress, and the response to that in the form of movement at the base of deformation marked on there. Now you could also for yourselves draw onto that what you might expect to be the movement in terms of glacier sliding, given that we've already seen that glacier sliding also relates to basal shear stress, and you could also superimpose on that, using your ability to calculate the shear stress through the thickness of the glacier, you should be able to add on to that an indication of what the shear stress looks like, and therefore what the shear strain, or what the creep profile looks like throughout the thickness of that model ice sheet. So you've learned a lot of stuff, as I say, already in this module, where you can understand how these components are tying together, and hopefully you can even add your own additional material. You could add your own material onto that graph to add more information about sliding and internal deformation. Now, one of the major points that we've made over these last few sessions is that there are driving forces, and I've indicated on this diagram, it's shear stress. This is all about shear stress, and if you're thinking about the bottom of the glacier, then it's the basal shear stress, and that's the key driving force, one of the key driving forces behind glacier motion. But we also need to think, as we have been doing, about controlling or resisting factors such as shear strength or friction at the base of a glacier, which is resisting movement that might be being caused by that shear stress. For example, in your last session with Dr. Waller, you were talking about subglacial deformation, and you will understand now on the basis of that session and your reading around it that the shear strength, the resistance, the ability of a material to resist that shear stress, the shear strength depends on factors such as cohesion and internal friction within the sediment. And it also depends on the effective normal stress. The normal stress, the vertical stress, the overburden pressure, and the word effective in the front of that means that we're taking account of water pressure, which compensates for that overburden. So in the little grey box there on the diagram, the effective normal stress or overburden pressure is the overburden pressure of the ice minus the water pressure. So a high water pressure, either at the base of the glacier if we're thinking about sliding, or in the case of subglacial deformation, a high pore water pressure is associated with low strength, low shear strength within the sediment, or low shear strength at that boundary if we're thinking about sliding. So hopefully, jumping around in your head right now, the idea is that, well, these are the same ideas, the same points coming up over and over again. Basal water pressure being really important there for subglacial deformation. Well, basal water pressure is really important for sliding. So hopefully you're thinking now of questions or points that we need to look into in a little bit more detail in the future sessions. For example, we need to think about water at the bed of the glacier. Or we need to think about the temperature at the bed of the glacier, which is one of the things that controls the availability and the behaviour of water at the bed. So as we're tying together some of these ideas from the last few sessions, hopefully it's giving you ideas for things that we need to look at in the next few sessions. So when that material comes along, you'll be ready for it, you'll be hoping for it, and there it will be, just at the point when you realise that you need it. So we've been talking about the driving factors, the driving forces, the driving stress, and we've also been talking about the controlling or the resisting factors. What I want to do now is say a little bit about how these dynamic characteristics of glaciers, things to do with the movement of glaciers, how do they relate to the shape or the profile or the morphology of an ice sheet or a glacier. And this diagram shows the cross sections, the profiles. So it's much like the previous diagram that I showed you, where you had an ice sheet cross section onto which we superimposed additional material. Well, likewise in this diagram, we have our ice sheet cross section, and the dotted line near to the top there is the theoretical cross section that you'd expect for a typical kind of driving shear stress. That's a typical kind of profile you would expect for a glacier surface, and you can see the thickness scale on the left hand side there and a distance scale in kilometres across the bottom of the graph there. So those upper lines, one is the theoretical cross section that you might expect of a typical glacier with 100 kilopascal driving stress, and also very close to that line are what are marked on there as a composite Greenland and a composite Antarctic lines. Think of those as being average cross sections through the edge of the Greenland ice sheet and through the edge of the Antarctic ice sheet, and you'll see that they fairly closely match the theoretical profile, which gives us some reassurance that our theory is working, because it matches the reality, the ground truth, if you like, from looking at the ice sheets. But then down at the bottom of the graph there are two additional lines marked Early Wisconsin and Late Wisconsin, and those are profiles that have been reconstructed for the Laurentide ice sheet, the ice sheet that covered much of North America in the last ice age. And the Early and Late Wisconsin are different time periods for that ice sheet. And you'll see that those lines have been marked with much lower driving stresses, 19 and 7 kilopascals. And at those lower driving stresses, the cross profiles of the ice sheet seem much lower. The ice is much thinner, and the ice has a much less steep gradient than it did at the higher stresses that we've put in for that we have for our current composite Greenland and Antarctic ice sheets, and we have for the theoretical ice sheet that we've got on there. So what this seems to be indicating is that there's a correlation such that the weaker sediment, for example, so a weak sediment at the substrate or a low friction substrate, is associated with a shallower ice sheet profile. Now, why might that be? Well, a first thought, and we'll look at this in a bit more detail over the next few minutes, but the first thought will be, well, maybe if we have a lower strength interface at the bed, whether it's a sliding interface or for subglacial deformation, the substrate, if that is weaker, then we don't actually need to push so hard in order to make it move. You don't need such a high driving stress in order to generate motion. So you can cope with a lower stress. Now you know that tau is rho gh sine alpha. I said you only needed a couple of equations in this module. That was one of them, and we're going to come back to that right now. Because if tau is rho gh sine alpha, and we're saying we have a lower tau, a lower shear stress, well, what's that going to go do to rho gh sine alpha? You know that rho is pretty much fixed. you know that G is pretty much fixed, but H, the thickness of the ice sheet, that can vary, and alpha, the surface gradient, that can vary. So how are those going to vary if we have higher or lower shear stresses? Think about that for a minute. So in order to elaborate a little bit on that relationship between the morphology and the dynamics, the shear stress and the ice sheet profile, we need to cover a couple of different topics. One is the idea of what we're going to call a perfectly plastic material, another is the idea of yield stress, and then when we've got those clear in our heads, we'll actually be doing some very basic, it is pretty basic stuff compared with the big numerical ice sheet models that you might be looking at in your reading, but we're actually going to do a very elementary form of ice sheet modelling by taking these factors into account that we already have in our heads: the shear stress equation, the idea of perfectly plastic material, and the idea of a yield stress. So let's talk first of all about the idea of a perfectly plastic material, and for that I'm going to go and draw on the whiteboard for you. So in the most basic, simplified, elementary kind of ice sheet modelling, we could assume that a glacier, ice in a glacier, conflating together all the different mechanisms of movement, we can assume that it behaves as what we call a perfectly plastic material. What's that mean? A perfectly plastic material is one where, as we increase the applied stress, for example tau in our tau equals rho g h times alpha equals a times tau to the n, etc. If we gradually increase the stress, in a perfectly plastic material, what happens to the strain or the movement is that initially, as we increase the stress, nothing happens. I'm not applying enough stress to actually generate any strain or any movement. I push a little bit harder, still nothing happens. But if I push hard enough, I reach a critical threshold point, and then as I increase the stress further, strain now occurs, movement now occurs, but it occurs all at once. It isn't that I now gradually increase the amount of strain as I increase the amount of stress, but what happens is that at that critical threshold, that's sufficient stress, I can't apply any more, that's sufficient to kick off the movement, and I get the motion in whatever it is that I'm applying the stress to. So at a low stress, there is zero strain, and then when I reach this particular threshold, then I get movement. And that threshold, that point on the stress axis, that's the yield stress. Now you can also think of that as being a strength. That's the ability of the system to resist a certain amount of stress before anything happens. In a stronger system, so a frozen bed or a very rough surface, for example, you might be able to apply, or you might have to apply, a greater amount of stress before you reach the threshold where strain occurs. In a weaker system, for example on a deformable substrate or a very well lubricated sliding surface, you might not need to apply so much stress in order to reach a threshold where the movement is initiated. So the yield stress is the amount of stress that you require for movement to occur, but it's also the maximum stress that you're going to reach, because once that movement occurs, once that amount of stress is achieved, then the movement occurs, and so you're not going to generate any more stress. And I'll explain that with a demonstration back on the bench. So you've got the idea of what we mean when we talk about yield stress. Let me just talk about that, let me just show you that in another way. So I've got a rock on the bench here. If I apply a force to that, I have to apply a certain amount of force, and then after I apply that force, it starts moving. So if I don't apply enough force, it doesn't move. If I apply more, it moves. But sometimes people have trouble envisaging why it is that I can't apply more stress and make it move more. What are we talking about when we talk about this limit to the amount of stress that we can apply? Well, let me demonstrate with a sponge. Now if there was a really big resistance to the movement of that rock, so basically if I hold the rock in place and I push the sponge against it, I push harder and harder and harder and I squeeze more and more and more, and I'm applying so much stress here that I'm squeezing that sponge up, and if I push harder I can squeeze it up more. So because I haven't managed to overcome this resistance, I can apply more and more and more and more and more stress to this sponge, or I can apply more stress at the interface. If you forget the sponge is there and I just apply that stress that I'm applying more and more and more, it's building up at the interface there, but we're demonstrating it by having the sponge there for you to see. Now suppose I take my hand away so we can now move this stone, and I start applying stress. Well, the sponge is squeezing up a little bit, but now the stone is moving. Look what happens to how much I'm able to squeeze up that sponge once the stone starts moving. I'm pushing harder, but the sponge doesn't squeeze up this time because the stone just runs away with me, runs away from me. So once I've overcome that initial threshold, which is what the yield stress is, once I overcome that threshold, then the amount of stress that I'm applying, the amount of compression that this sponge is suffering, which is a marker of that stress, that doesn't increase anymore. It stays at the same level. And if I try to push harder, the thing just moves away further. So I can't actually increase the stress on that sponge because the stone runs away from it. So that's why on that graph, we increase the stress to a certain point, and then at that critical yield stress threshold, I can't push it beyond that. I can't increase it beyond that point. So that's why for this situation, once the rock is moving away from me, I know what my tau shear stress is because it's the yield stress, and it's going to be at that level as I continue pushing. So I've fixed tau, or if we're talking about sliding, I've fixed tau b for my dynamic situation. So when I'm filling in my equation now, well, tau b is fixed, and if I have a very low friction or lubricated bed situation, that yield stress, the tau, the force I'm having to apply, is going to be relatively low. If I have a higher friction situation, so I don't have a deforming bed, I have low water pressure, the glacier is frozen to the base, it's very rough, in that situation I have to apply a higher shear stress. So I've got more compression in the sponge, but I'm applying a higher stress to make that movement happen. So I can be applying a low amount of stress in order to make things happen. If I have a weak bed, I have to apply more stress, so I have a higher tau if I have a strong bed. So the yield stress depends on a number of different factors. For example, the deformability of the bed, the temperature of the ice, water lubrication at the bed for sliding, basal water pressure, debris within the base ice, friction, all sorts of different factors control that. But it's an assemblage of those factors, if you like, which are giving us this broad value that in a simplification for this kind of basic modelling, we're taking as being the point at which movement occurs. So yield stress is going to be low for a deformable or low friction bed, and the yield stress is going to be high for a rigid bed or for a high friction bed. So this is fixing the value tau in our equation tau equals rho gh sine alpha that you're familiar with. What we're saying is that in any particular glaciological situation where a glacier is moving across its bed or moving across its substrate, then tau, well, that's going to be the yield stress value. Whatever that value is that you need to achieve to generate movement, well then that's what the shear stress is going to be that's generating the movement that you've got. Now we know that rho and g are effectively fixed, the density of ice and the force of gravity they're effectively fixed as well. So if we're fixing tau at a particular value, in order to accommodate that we have to adjust either h or alpha, or both of them, the thickness of the ice or the gradient of the ice surface. They're the factors that can be adjusted to accommodate a given value of tau. So if we were to change the value of tau, if we make the bed suddenly become weaker or suddenly become stronger, that change is going to have to be accommodated by a change in the ice thickness or the gradient. So suppose, for example, we have a glacier resting on a frozen substrate, but then that substrate melts and becomes easy to deform. Well, then we go from a high yield stress situation with the frozen substrate, where you'd expect, because of the high yield stress, you're going to be expecting a thick and a steep glacier because the shear stress, the yield stress is high, and we're suddenly now going to a low yield stress situation where we have a mobile bed, and to accommodate that, in order to reduce the value of tau, to accommodate this reduced value of tau, either one or both of the thickness and the gradient are going to need to change. So we'll end up with a lower gradient, thinner glacier if we have a lower driving shear stress. So if you imagine for a minute my imaginary ice sheet where I have a steep slopes and I have thick ice because I have a rigid or a frozen non-deforming substrate, and then I change the characteristics of my substrate for some reason, and so perhaps because of the overburden pressure or because of something happening underneath the glacier, we lower the friction, we reduce the yield stress, reduce the required driving stress to accomplish movement. There, what's going to happen is that the thickness of the glacier is going to retreat, is going to reduce, the gradient is going to reduce, and what that equates to, and it's perfectly common sense if you think what's happening to glacier motion on a more deformable or a less rigid substrate, we're going to change the profile of that glacier so it stops being thick and steep and it becomes more spread out, thinner and lower gradient. Now, if we're not changing the volume of the ice at all, so this isn't a mass balance issue, it's purely a dynamics issue, how much we're spreading the material out or keeping it contained in. If we're not changing the volume, but we're reducing the thickness and we're reducing the gradient, well, as you can see what I just did in drawing it, inevitably the drawing resulted in me spreading out the edges of my ice sheet. If I then did the reverse and I froze up my bed, or I removed the basal water, reduced the basal water pressure somehow, but just something to do with the subglacial drainage, not a climate-related thing, but a change in the dynamics or a change in the subglacial hydrology, and now I'm increasing the yield stress by hardening up the bed, well then we're going to revert back to our first cross profile there. The glacier is going to grow thicker, it's going to get steeper, and the margin is going to retreat. And so you can imagine a series of advances and retreats being associated not with anything to do with climate, but associated with things to do with basal conditions. Now, as part of the reading that I'd like you to do associated with this, look up binge purge oscillations of the Laurentide ice sheet. That's some work that was done by Doug McHale a while ago, and it talks about this idea of shifting from one ice sheet profile to another as a result of changes in bed conditions resulting in the expansion, periodic expansion of the ice sheet. And this also explains the graph that we looked at earlier that showed the low cross profile, the low gradient, the thin ice associated with sections of the Laurentide ice sheet in the last ice age that we can tie to low yield stress bed conditions. So what we've been doing is just taking your basic knowledge, tau equals rho GH sine alpha, you've known that now for 4 weeks, just taking those terms and now gradually learning a little bit about how glaciers move. You can use that to figure out some very basic ice sheet modelling where you're predicting what's going to happen to ice sheet morphology, the shape or profile of an ice sheet, based on your understanding of things that are happening in ice sheet dynamics, things to do with the movement of the glacier. And what I'd like you to do between sessions this time is just play around a little bit with ideas about what would happen if you varied some of these conditions in that equation, but think about it in real world terms of varying the friction at the base of the glacier, or varying the pore water pressure in a deformable subglacial sediment, or changing the roughness of the glacier bed as a result of glacier erosion processes. What's going to happen in the long run? If the glacier is eroding its substrate, that's going to change the characteristics of the ice bed interface. What impact is that going to have? And could that be another way in which glaciers cause, by their internal dynamics, how they cause non-climate related glacier fluctuations, as well as obviously the really important climate-related glacier fluctuations that are related to mass balance and that we'll talk about later on in the course as well. So there's lots of things for you to be thinking about at this stage, and lots of ideas for you to be tying together in this big conceptual map that you're drawing of how everything works together, how everything hangs together in glaciology, glacier dynamics, ice sheet morphology, connections to the big global system, and connections looking forward over the next few weeks through basal thermal regime, glacier hydrology, all the way through to geomorphology. And as always, there's reading for you to do, and as always in this module, I'll suggest you start with reading a little bit of the basic stuff from my old textbook just to get you started, and then you can move on from that into more advanced sources to give you more detailed and more up-to-date information on top of what you're getting from the basic textbook.